Working, I believe it is. It looks like it is. Then. Testing microphone. I believe it is working. It's working somehow. I have a feeling that the microphone that we had is one of these things that's still on and in there from the quality of the sound. That's what it sounds like, right?
I mean, when I was listening last week, it sounded fine.
It sounded fine last week.
I don't know if the Zoom is different than when it records. I don't know if Zoom.
Maybe the speaker here that was playing funny. Maybe the recording is better than the. Okay, so last week, that's good. Wrong. Oh, green board. They've it's 5. And so last week, we had done things on 1D and also for 2D under a strip footing. So we had considered with the same formula using beta and delta. We had used it to calculate the stress distribution under the center of the strip footing. To do it in 1D, assuming double drainage. And that's the white, well, different times. So the dotted line is the maximum. And okay, so if I go now, I've used so this is the maximum, and if we as the time progresses, you can see the difference between under the center between 1D and 2D. And you get one thing that you can see is that it dissipates faster with the 2D than 1D, as you would expect, because 1D you don't have that lateral escape, right? So and also you will see much more increase of the pressure down the center in 1D, because in 2D it's allowed to go sideways, while in 1D it can only go vertically. And so you get that increased pressure there, see, above the original line in 1D until the little crest basically reaches the midpoint, at which point you get a similar shape as so that's the difference. So what I did, I believe it was yeah, this equation was incorrect. Accidentally, I mistyped it when copying. I had sine, and then I missed it. Instead of sine beta, I had sine of beta plus two delta instead of this multiplication here. It was a mistake, so looking at this. But one thing that so by just copying and pasting, you might find it interesting to have a look. So this is at time zero. We have we have our stress initial pore pressure distribution. So the excess pore pressure, maximum right under. So this is the center of symmetry on the far left. Maximum pore pressure right under the footing. With the bulb and going to zero really quickly. And then as we progress in time, you can see the diffusion of that excess pore pressure. It becomes smaller in absolute magnitude, but diffuses a little bit more. You see the shape until eventually it looks a little bit like just the evolution and the spread of that pressure. So this is the 2D kind of representation of our that. So this one was just copying. If you recall, we were just doing copy paste, right? We were running a macro that handled the copy paste for us in a very convenient way. And it's basically from those that we've generated this chart here that we can then step through and just take different values at different points. I'll be posting that spreadsheet also on Brightspace if you want to have a look at it. Okay, so today we're going to be looking at the axis symmetric, because what if we want to represent the pressure distribution over time under a circular loaded area or any shape where we have axial symmetry? Usually it will be under a circular load or a circular face, because axis symmetry assumes that in every direction you have the same. So one thing that you cannot have in axis symmetry is a realistic underground seepage regime, right? You cannot have, because it's axis symmetrical, so it assumes symmetry. Everything is the same from the center of your symmetry radially, right? So you can have horizontal ground layers. If they're not horizontal, it implies that you have like a conical. So if there's a slope, then it's conical, and even if it's comes back up, you know, it assumes a symmetry everywhere. So usually if you have soil layering, it will tend to be most of the time horizontal, because it's the less weird kind of scenario when you're considering axis symmetry. But it has the advantage of being a pseudo 3D without going full 3D, because it assumes axial symmetry. It should be more like 3D than 2D. So let's see which one was the file. that's basically what we ended up with last time. So that was the example we considered and we analyzed, that the one we just saw, that spreadsheet, where we had a footing, it was 2 meters, so it's 1 meter on each side. And we had considered no flow boundary at the axis of symmetry. Here also was not axis symmetric, but we'd still taken advantage of symmetry to basically cut in half our domain. Because otherwise we would have to have the same thing on the other side. So taking advantage of symmetry is something you should do whenever it's applicable, convenient. I could not have done it if I had a very detailed layering below the footing, right? If I had different layers that are not purely horizontal, if they had some kind of slope to them at some point, then I would have had to make a full 2D. I was able to use symmetry because I had a uniform soil, and so in any direction, things would be working right. And these figures are basically what we get from. Now, what happens when we want to represent something in terms of axis symmetry? Axis symmetry is what we use when we want to represent the symmetrical scenario. Again, in a uniform soil, perfect scenario to represent it, to use it. When you're looking at a well analysis and so on, it works fine then too. Now you have so we're going to do the same thing. We're going to do again consolidation in our case, but we're going to look at it from an axis symmetrical point of view. So now we can look at as well, it will be axis symmetrical from that center. The loading, we're going to see a way of adding loading that could work for any kind of loading, but because it's an axis symmetric problem, it will have to be kind of a circular in that sense. But I want to show a little trick with the basic definition of Boussinet that can be used for any kind and shape of loading pattern if you have the coordinates of your area. So again, we start like we did last time. We define the change of water content is the rate of change of volume of water over total volume over an increment of time. And so we can have the change of volume over time, which is a change of flow. And we'll call it minus because it's if it leaves, it decreases. We'll call positive going away from the center of symmetry, basically. And so the volume in terms of a cylindrical element is, so it's R. Okay, so we need the radius to be able to size the length of this side. So the axis, okay, so the width of our element is R d theta, because that's the length of the arc, right? The length of the arc is R d theta, and the width is dr. And of course, the height being dz, if z is our elevation. Okay, so we have R d theta dr. And usually those elements will always be vertical, okay? To have axis symmetry, when you have fluid flow, it doesn't need to be vertical when we're dealing with heat transfer, for instance, right? But why do I say that it needs to be vertical when we're dealing with seepage? Why can you not have a horizontal cylinder with axis symmetry when we're dealing with this type of problem?
horizontal, like a cylinder going with this.
Yeah, you could not think of squishing, of measuring consolidation, say on a cylinder that you're squishing horizontally. Why? Can you not use excess symmetry in that case? But you could simulate the heat transfer in a horizontal bar or a vertical bar. But you could not do the same. What would break symmetry in the case of water movement in that case? What can you not just arbitrarily reorient that controls water flow? Yes. Gravity points in one direction, and so if you turn your cylinder sideways, you no longer have a symmetrical, so you cannot have your, you would have the force going in one direction along the radius and perpendicular to the radius, so you're breaking symmetry. Okay, so for anything that involves weight of something or gravity, you have to have a vertical cylinder, okay? So just keep that in mind. But for things like, it's pure diffusion without, taking into account the advection into the water stream, then, sure, you could have a horizontal cylinder, or in any inclination, and the same thing with heat transfer. So in our case, it's strictly vertical, and so the delta Z here represent the change in elevation. So that's how we express our volume. And we go as we did before. This time we look at the water that goes into the element. Right? Radially, we'll go through this face and leave through that face. So in the radial direction. So we'll have the area on the inside face, so R minus half dr, d theta times dz, and R plus 1/2 dr on the outside. So the key here is that you have a constant flow, but it's going through a medium that is changing size across the element. It may be small, it's half of the delta R, but it is increasing in size. Okay, so there is a directionality in that sense. So you have your flow in and your flow out, and if you substitute in your equations radially again, basically is the change in water content. In the radial direction minus the change of water content in the Z direction. The Z direction is straightforward because it's a constant area. That's why this term here doesn't change. It's just a constant area in that direction. Okay, but basically you express the Q, little q is the Darcy flux, basically. The Darcy flux in the radial direction. And you end up with an interesting term by just doing a little bit of algebra. Now, we end up with QR, which is the Darcy flux, so K radial, KR, dH over dr. And so if we replace in terms of hydraulic head, we have K radial direction times d squared H over dr squared. This term will look familiar, but then we'll have a term that is not second order, it's first order, and divided by R. Okay? So the distance will be important at that point. And the other part is basically the similar as what we had before. And so now, if you have multiple soils, so for a uniform soil, this is good enough. For or you can distribute KR into the equation. For varied soil, don't forget that you need to keep your K inside the differential function there. So a first example here that we have is a one diameter well, a 1 meter diameter or a radius. It was supposed to be intended to be a radius. It's dug into a clay layer that is 8 meter thick and has a isotropic hydraulic conductivity. Here we're gonna look first at steady state, I guess, so, but using the axisymmetric formulation, basically. So we'll have to look at the hydraulic head within the clay layer at steady state if we're looking at the hydraulic head in the well. It is brought down to a depth of 5 meters. While initially it was 1 meter below the ground surface. So we'll have an initial hydraulic elevation in the soil. So at steady state, one thing that we can say is that the change of water content over time is 0. And since the soil is uniform and isotropic, we're going to assume that Kr is equal to Kz. That is constant. So again, we go into the development of the formula. The main difference here is that, so this is centered on Ij in all cases. We go to radially, we're going horizontally, so it's based on the column I. While delta Z is vertical, so it's based on the neighbors on the row J. And so we have this term which is equal to 0. So again, it will be basically a little game of isolating Hij based on the neighbors in this particular case. Okay, and so we end up with a less straightforward problem expression in this case. Okay, so we'll do it. I was thinking maybe doing the consolidation first before we tackle this with a numerical example. But basically, this is what we're going to have when we try to solve the steady state problem. Okay, we're going to have to define our increment and the R direction and Z direction, which we can keep equal. Our life's easier. But even if we keep that equal, we'll have delta R to the fourth, or delta Z to the fourth divided by 2 delta Z squared. So basically that will be 4 times. So 1/4 of delta R, or delta R squared divided by 4, basically is what that term will reduce to. And then because we have delta Z here, so sure we can multiply it here and isolate it. We can also isolate it on this term, but there will still remain one term here where we won't be able to fully isolate it. And so there will still be a term that has a delta R product and divided by R. So the position will need to be taken into account. And so in the previous example, only the interval was important, only the delta. But for axisymmetric, you need to keep track of your actual position in the radial direction because you have that term here. See, these other two terms, they look exactly like what we had before, right? We're doing our steady state problems. And we just had to, so basically we ended up multiplying delta R squared by here, which canceled here, it cancels here. So it's the average of the neighbors, but the last term will still have a delta R left over divided by R. And that's what will change,
It's
yes,
kind of like stress concentration of the perfect solid.
yeah, basically.
So does that? Actually, no.
Anyways, we'll work on the well problem after, but I think it's more interesting if we start with the consolidation axisymmetric problem because we just came out of the strip footing. So we're going to basically be trying to adapt the same and look at the same problem and have a look at our pictures. So if we are basing our work on the development of the consolidation equation, again, we use the same equation that we just developed. Now we have horizontal, which is equal to our axial coefficient of consolidation, and z squared u. And again, we have the term here, which is the axisymmetric component of the whole setup and the vertical component. So the only part that is axisymmetric is CH times one over R over dr. So that one is the first order problem. Obviously, for a uniform soil, we don't need to worry about the changes of coefficient of consolidation within the soil. So we could still have it be not as isotropic, but in this case, it will also be the same solid. But if it was an heterogeneous soil, we would have to define it more specifically and include the coefficient of consolidation inside the variable there. Of course, multiply it and give it. I think I'm missing one zero from there. So yeah, we're missing CH over R. So we are going back to our nice little problem. We have a 50 kPa water tank this time instead of a strip footing. 2 meter in diameter, the same width, the same as the width of our strip footing. And we impose a stress increase of 50 kPa at the surface. And now we're asked to find the excess pore water pressure, the degree of consolidation. I have here, okay, but now I have to go on a slide with the equations. Okay. So we have our coefficient of consolidation of interest, which is nice. So what I'd like to do, this is what I forgot to include in those slides, is start with the equation to express the stress distribution under the center of a circular loaded area. And we're going to repeat again the problem in 1D. Because I don't think it would be fair to compare it to the 1D strip footing distribution unless we have also this one to add to it. Just give me a sec. I will go and
assume no plate flexure under loading at all.
No. We're not being fancy here. You, whenever you're building a numerical model, okay, little tip, always start with the simplest assumptions, okay? Once you got something, it works, then you start adding complexity, okay? Don't start by imagining all the most complex scenario and try to, you will get discouraged and will abandon any kind of, so numerical modeling, or you start simple, you test it, you add complexity, test it, add another level, add one element of complexity at a time. Don't never try to do everything at once, because then when something breaks, you don't know what broke. Okay, so always start from simple, add one element at a time, make it gradually more complex. And figure out which one is meaningful. You may find that some element of complexity that you thought might be important turns out to be, I mean, it becomes unmeasurable in practice, or it's so small that it's basically not even worth modeling. You're spending too much time simulating it. So by adding complexity one element at a time, you can determine what is meaningful and what's not. Yeah.
Conceptual question, but if you find something to not unmeasurable after testing and integrating it, say this is relatively insignificant, you keep it there so that say you
You
bring.
don't need to keep it in future. It depends on the complexity of the simulations, right? But it might be relevant in some scenarios, so you may not want to discard it completely. But you may want to test which scenarios, you may want to try to do sensitivity analysis to try to see what scenarios that would be more impactful in. And you say, well, we may introduce it when we're considering these type of problems, but not when we're considering these types of problems. So it might be a valid research in itself. If you find that it's not meaningful, oh, maybe now I can write a paper just on trying to see when it's not meaningful, and are there scenarios when it becomes meaningful where people should be aware of it. It can be a paper on its own. Right? Trying to figure out what it does contribute, when would it make a difference and when not. That's also because sometimes it may happen. Center, trying to find. Circular. This is. So integrating Bussine, I think this is what you get for the for the stress distribution. Assuming that my function is without errors because I don't memorize this equation for the fun of it, usually. So we're gonna make that assumption and look at how it looks like compared to what we will get from the strip footing in 1D, right? We'll try to solve the problem again in 1D for this particular case. I may keep it here for now. Just to have a comparison, and then we'll take that one sheet and put it elsewhere. What do you think? Make sense? I'll try it for now. This is 1B. Particular 1B. Oh, we crashed. No. Ram. Um, Circular 1D. The diameter will be the same, so meter Q naught will be 50 kPa, so that will not change. What we need, equation nearby. So we will have first an expression of the depth. And then we will be calculating, oh, yes, that's one thing. Let's reduce delta T to reduce. 1 month, or increase it to 1 month instead of 2 weeks. We'll take the 1 month that we had used for the 1 week problem. I think we'll do it up. So we will have our depth is going to be the same as here. fluid at every half meter increment up to 8 meters. What else do we need to have? We need to have the stress at time zero, so before any changes. So we have here Q. Make sure that I have the expression for this. I believe the R here will be the radius, right? B over two. And it's constant. No problem. So we will use Q naught times 1 minus 1 over 2 times 3. One power of halves. And can have a conditional if zero, then okay. 1D, hopefully the stress distribution on the circle. That's let's call this initial circular. X value stress. And so already we see just from the just from the shape of the initial stress that that's something that is meaningfully different. Because it's a circular loaded area. And as you can expect, so why why the shapes are different, you think, from the initial conditions? Just. Why? So the dotted lines are the initial for the. For the axisymmetric. Not axisymmetric, but for the, they are both 1D, but one is for the strip footing and the other one is circular load. So why the stress distribution with depth is so different? Does it make sense intuitively? Because this is another thing that you have to think about, okay? When you're doing numerical methods, don't forget that your objective is to represent a physical scenario. Okay? So you can make mistakes, equations are nice, but equations are equations, you can mistype them. The model can be wrong, or you may have made a typo. So when you look at something like this, you should always think, does it make sense? Does the difference between these two dotted line make sense?
Yeah,
Why?
because you have radial spreading impacting the quantity solution. Those. This loaded at 30.
Okay, so in terms of width, they're both the same dimension, right? They have the same diameter.
And the circular one is smaller than the square one.
Yes, the circular one is finite perpendicular to the plane, right? It's finite, so the stress, because it distributes laterally, it adds up, so the points that are over in the distance, they add stresses here, so you should expect the strip footing to be larger at any depth. Except right under the load. See, right under the loaded area, they're exactly the same value, 50 kPa. But the strip footing, because it has contributions from so many points in the distance, infinity, so it takes longer to reduce. Because it has more the length. So we're assuming that they add up because of linear elasticity, but they add up with depth, you know, you have the projection of the cone, of the bulb. And so they add up. So it makes sense. You would expect the strip footing to be larger at any depth. Okay. So right there, okay, I'm happy with that initial distribution. So if we were doing 1D, it would look exactly like the 1D in principle. It's basically, I mean, we're going to do explicit 1D basically, but on the circular distribution. So if we were to do 1D instead of 2D, we don't consider axis symmetry, right? Axis symmetry is something when we do in a pseudo 2D on a 2D that mimics 3D, right? So, but you should expect to have similar shapes as our. So in this particular one, I will remove the 2D because here we're going to be comparing specifically the 1D at different times. I mean, this is not the correct curve, it's just because I used the chart type smooth. It's because I didn't like the sharp points. But see, that's why I smoothed it to have look, but on the first iteration, it looks super, it adds because of the curvature. There's a way, I forget how it's called right now. But you can improve your boundary condition by changing the spacing of your, instead of having constant spacing. One thing that people like to do, if you assume a constant number, say you want to use the same 20 or so, the same number of space of intervals. But you assume that you're doing it on a 180 degrees half circle. Okay, so you find the sine. So you make 180 degrees of constant angular. Correct. So you divide the 180 degrees. And even a constant number of angles of constant size and a given number of angles, all the same side. Then you find the sine. And so when you're at 180, you'll have the full length of the position here. And that means that you will have smaller increments on the edges and larger increments near the center, which avoids when you do a smoothing like that, like I just did, it will avoid those edge effects. Interpolations. And this is a polynomial interpolation, basically. And if you want to avoid those crazy unphysical interpolation, so when I use here the smoothing, sorry, type. That little edge there that I get is non-physical, right? It's just because of my polynomial interpolation that I use in the smoothing curve. And that's why we get this increase here. I mean, it disappears quickly after the other steps. Eventually, it becomes irrelevant. So, but keep that in mind if you're doing publications and things like that, and you're using some nice polynomial smoothing. You want to sample it so that you have your edges more constant. And the best way to do it is to use kind of over the range, go into a hemispherical or hemicircular.
How would you be able to tell overshooting if you're not the surface? Cause it's like an overshooting fit, right?
Yeah, this is just a polynomial. It's basically using a spline. It's a cubic, right? That we use as a cubic spline. But because it's a polynomial, basically fitted that to those few data, you will get those weird shapes sometimes at the edges. So the one way, as I said, that has been found to avoid those things is a sampling using a hemicircle over the range. Because if you have, let me do it. Should remember that this is being recorded, so I should do things on here and not on the physical boards. It's hard to remember that. So if I have a range. Do my sampling, I should do it from the center of the range. So let's say that I want to. And so these 2 points are represent the range over which I want to sample. Okay? So I should have identified the center first, but we'll work on it. Got a center there. A circle. I divide the circle in equal parts. Angular wise. So I want to know where should I put my samples game. No, that cost. Unfortunately, this is detailed sampling as I can get for now. So So these are the points where I would, so you see my spacing is wider near the center, a big, smaller, smaller. But if I add more equidistant values, it would be even more obvious. Let's see if I can make an attempt. And reasonable halving is the interval. And then these are half of these. Close enough, right? So I do the same thing. In this case, I use so the cosine is cosine of the angle times the radius with the maximum half distance or would give me my spacing. So now okay, if I did rid of my array lag here. And we measure all the same height. Give us an idea of what we did on the spacing this time. Focus on the spacing rather than the height of the things. And so that's the kind of spacing I would want in my data. Be able to have smooth curves that avoid those weird things. So if I generate my simulation at points that are spaced like this, and then do my smooth curving thing, because of that spacing, I will not get those.
So why does the semicircular pattern?
Just because of the nature of the circle. Probably pi has something to do with everything. But no, it's just the nature of how the spacing changes, right? It's using those trigonometric relationships. So it's the cosine here, but as you go from one end where you're, think of it like,
So say you have 2 points.
yeah.
So the point here is up top, and as you move forward, the spacing increases and then decreases.
Yes, it increases towards the center. Towards the center where you have more points balanced on each side. So it's less sensitive to small changes because you have a lot of points on both sides, right? So doing your smoothing, things work nicely. But when you get to the edge, you're losing information from one side, so you capture better the transition. And that has been shown to give the best results whenever you're trying to, so if you need to do sampling for things that may be used and you want to have nice graph, and you can control the spacing, doesn't need to be constant. This is the strategy that will give you the nicest results. Okay? Those are one of the some of the little tricks that you use, and so I don't know if it's really we really need to go into the workings because the explicit, it will still be the same as we did last time in terms of explicit. The only difference is that we will start from instead of starting from this dotted line, we start from this one. So maybe we'll just move on and see how it compares with the for that one, we may want to do the solution. In this case, it was just to compare the initial state. Because we should expect there to be a difference. So we know for a fact that there will be a difference in our predictions in this sense. So The question that we have to ask ourselves though, when we're going to do a loading like this, is how do we load? How do I express my my load? Okay, because one of the things that you discover early on when you do you look at Boussinet is that there's no closed form solution. So if you want to do axisymmetric or 2D, 3D, you have to be aware that there's no closed form solution available to express the state of the stress anywhere below a circular loaded area, except directly under the center or directly under the edge. Anywhere else below or outside does not have a closed form solution. Okay? So what are we going to do? What strategy are we going to use as numerical tinkerers to be able to express this?
Could you repeat? I just missed.
Hmm?
Could you repeat again?
Yes. So there is no closed form solution. So you remember when we have the initial conditions here. We want to calculate the initial state of stress. So this is the state of stress, basically, or the pore pressure increase at time zero, right? That's caused by the addition of the total stress. We're able to calculate the stress here and there and there and there. But for a circular loaded area, we only have a closed form solution. So we have a uniform load in the shape of a circle over an area. There's only a closed form solution to evaluate it under the center or under the edge of the circular loaded area. Those are the only closed form solutions we can find. Here we had that fancy thing with delta and beta, you remember? And with delta and beta, we could calculate it anywhere. But
They're saying we can only calculate.
we can only calculate it along this line or along the edge. That's a problem, right? Answer is yes, it's a problem.
Yeah.
Oh no. Are we doomed? What possibly can we do?
Well, we can place it along the center and edge. Good. Carefully.
What is the basic function, the Boussinet equation, the starting point of all the Boussinet formula?
We can start at that point.
It's the stress under
Yes.
concentrated load, right? On the point load.
So you apply a point load at different instances.
Okay, so yeah, you can make your own grid that doesn't need to have the same spacing, it can be much more refined than this, right? You make a grid of point loads, divide the loaded area. So in this case, it would be, so we'll use another sheet where we'll define our coordinate X and Y. This time it will really be Y, not Z, right? Or not the zeta, if zeta is the depth and Z is the elevation. So, but the X will match. That's important. The X should match your X here. The X is the radial distance, basically on one plane.
If we had a distributed load of capacity,
Yes, it's a distributed load. Because it's a circular loaded area, just don't have the. You could also do it under the corner of a rectangular loaded area. If you were using Bussinet, it could be another option. Then you combine, but the equations are more complicated. So numerical integration, basically, of single points would work for us.
You're saying computed at every point along the surface?
Well, you just need to have a number of points X and Y that define the entire circle. Right? And at each point, you assign a value of a load. So basically the stress times the area of the little squares, right? So you have now point loads and a finite number of point loads describing the shape that you want. The advantage of that technique is that you can have an embankment of any shape and size, and you can have arbitrary now loading by doing it this way. You can take a picture, a shaded relief map, kind of express the elevation. So in our case, we have a circle of a radius of 2 meters. So let's begin with a new sheet. I think. This one will be through the okay. Variables will have B, which is the diameter, 2 meters. We have Q naught, which is 50 kPa. So we'll go, what will be our interval? What will be our delta X and delta Y? We will make it equal. Delta X and then delta Y, and we'll have delta. So we'll use delta X and delta Y. Delta Z will be 0.5 meters. No, this is not the delta Y that we, or this delta X, let's just say will be. I'm hesitating, should I call it R or? I will call a rho the radius. Delta rho. Not confuse it with R, which is our little constant in our equations. Um, So delta rho will be for the 2D simulation. Delta X and delta Y is just for our load distributions. Okay, so these, although that X conceptually, okay. Want to show you what my issue is here. I'm trying to represent a circle seen from above. And basically, if I represent this is the top view of our plane of symmetry. Okay, this line here goes to the center of the circle and represents the radial distance. Okay, so this is our rho axis, or another, yeah, our rho axis. I have this axis for rho. So we will define the load based on this on our sheet. On our loaded area. And when we look at our plane in 2D, our axisymmetric plane will be basically a vertical slice. Okay, so that line there is this plane here shown as a single line. Okay, we're just cutting. This is just a cutting from there. This is symmetric. So here our coordinate will be rho and Z. This one will be Z. And rho. While here, our coordinates are X and Y. So X is superimposed on rho, but conceptually it's different, okay? Conceptually it will be different because it's going to have a different delta X and delta Z, okay? So X is always in that direction, right? While rho is always radial, okay? So conceptually they are different. And so X and Y only exist on the top, on the ground surface plane. Okay, so they're perpendicular to, they're on this plane here. That's flat and horizontal. So just to keep things separate in our conceptual basis. Okay, so that's why I'm calling here delta rho and delta Z. This one will be equal to each other. And this one, we can afford to make them smaller if we want. Why smaller? What's the advantage of making those smaller? We get a little bit more of granularity for the distribution of stress below the loaded area. We have multiple. points. So. Okay, but you will see that it does add some kind of complexity. Okay. So I think for today, that's what we'll end is expressing our loading in this way. Because you have to visualize things in two different components, right? To combine them. So here we'll just have the X and here we'll have the Y. I want to keep it a little bit, so X will go from what? From -1 to 1, right? Delta X. So it doesn't need to be as that big, it just needs to cover the area where you will have points. And 0, again, we start at 1, and Y will go from will go from 1 to -1. Okay, and the center of symmetry will be at 0. So now we will define an area. It's easier to define it rectangularly. I mean, we could have more specific points that are only exist on the circle. But one thing that we can say here is that we can find, I will define this as X. It will be easier, and this as Y. But I will make sure to define them just in case I wanted to add other sheets. I will, see, this is one thing you cannot do in Excel, by the way. You see what I did here? I defined the X variable by just changing the name here, right? And I did the same thing with the Y. Now in LibreOffice, what I can do now is go to Control F3, find X and Y and change the scope and say it's just for loaded area. In Excel, you have to define the scope at definition time. So you would have to go to Control F3 first, say add variable X and define the range manually. You cannot use the simple way of doing it. So this is, so now what can I say is I can have square root of X. So let's say that I just put X, see wherever I put X, it will put the value of X wherever I am on the sheet, right? And if I say Y, it puts the correct value of Y wherever I am. See, that's a very easy way of doing it. So if I say square root of X squared plus Y squared, I get square root. And already you can see 1 defining the shape of a circle here. So one cool thing you can do with this trick is that we can say if square root of X squared plus Y squared is larger than is it E/2? Then 0, otherwise Q naught. And here there's a problem, we'll discuss it. I want to have the load. We'll have to change the coordinates, but. You start seeing, one thing that we can do here. Which is basically. If I say additional formatting. Format. So we get our nice loaded area that looks like a circle. Um. The real question we'll have to ask ourselves is, do we want to have the X and Y here? Of the center of the little squares around our knots. In that case, we should go by offset by half of our delta. Yeah, I should start at 1 plus half delta. So the first one should be -1 minus 0.5 times delta x. Want to go above. And here we want to have and that way, that is the coordinate of the application of the center load. So we don't have 0 exactly, but 0 will be found somewhere in between. So we have minus 0.05 and plus 0.05. So now we have the coordinate of the center application of the load. So instead of having 50, we could say Q naught times delta X times delta Y in terms of our load. Times delta delta Y to delta X times delta Y. We define X and Y. X. So. Okay, so now that's the point load at the center of. And now. This is nice, but what we really want to have is a single array. Remember, we want a single array. This is a nice representation but we would like to have it in terms of a single array of X, Y. And then value, so X, Y, surface load, surface load. So which can be 0 or 0.5 basically, and just have a single array like that. Then we can do a summation of the stresses at each point. So we'll take a short break here. We'll see how we implement that on a spreadsheet after the break. Because I need to refresh myself. And then we'll just try to set that up quickly, just so we can get the initial starting load. And next time we'll see how it finishes and how it comes. The other one, again with the axisymmetric difference. Sounds good? So just let me go. The pressure. Back. Oh, yeah, the stream was live. So
Also,
yes,
I do not understand why you increase that 0.5 delta Z.
that's multiplied by, this is just my loaded area. This is just a visual representation of my loaded area.
You're creating a 2D surface.
Yeah, this is just conceptual. I don't need this. Okay, but conceptually it helps me. You could also create an image, a loaded image, right? If you have a complex geometry, you could have a series of buildings and each one could have a different loading. But you could still add their weight together.
Will you take each slice, individual slice? Or-
Well, no, our point, okay, our point is here. We start at 0, 0, which is right between these two lines and between these two, right? So we have a plane that's coming through right here. We'll have a plane. So at each depth below that plane, at each point, we're gonna add, we're gonna say, it's the sum of all these times the depth at which I am. Da, 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 da. So, you'll have to do a calculation of your position. So we have to look at the Lucines formula for the stress under, a point load. And then, but first we need to express those as a simple array. Okay, so this can be an image, okay? I could have imported this from an image in terms of how we convert the data. But the thing is, I have loads, I have values in an array, in a rectangular array that goes from an initial coordinate to a last coordinate and something, same thing in the other direction, right? So, let's say image. Let's just say, calls and rows. Okay. Uh, Check this. And so X got loaded array. Okay, so I'm just counting columns of the X and row of the Y. In this case, just to define. The number of rows and the number of columns. Okay, now we'll have, the load. And express it in terms of X, Y, and how will we express the load? So I want to get every single point in my array and convert it. So this is an important little trick that you will often use in when you're generating data like this automatically in programming, even when you're programming actually particularly. So you need to be able to convert that grid into a sequence, right? So we want to go row by row. So we will have, what we want to have, so we want to, we we want to break it into each row. Let's call this data area. Then we'll go extract the node from the data area. So, but we want to know where to go. I'll have here just an index indicator here. We want to go to 483. That's gonna be 484 points. Because I have 22 times 22. Or I can have here max index is going to be n rows times n columns. Because I start at 0 cement. My maximum index will be 483, what I'm looking at having here. Okay, sounds good. So I'll just keep that in mind. And so here, what I really want to do is generate a looping. So here I want to have the X moving. So it will be my index or modulo of my index number of columns. So I wanted to go from 0 to 21, 0, 21, 0, 21, 0, 21, and that's nice, but it's not the proper value, right? So it should be that times my delta x, right? That's already better, but it's not starting at 0. So it has to be plus, let's call it index, for the area. Value. Minus 1.05 to 1.5, and then we loop starting again. So that looks to be okay. Let's see if it's doing that. We should finish it. Yep. Okay. So we have that loop. Just doing vroom, vroom. Yeah. So by using modulo operator, we're able to do the loop from the index that just loops from 0 to the maximum number of index. So what's the maximum number of index is the number of columns times the number of rows minus 1 because we're starting at 0. And most programming languages start at 0 their arrays, so it's not a bad habit to have. So this is the index. This index here is the pointer that you would use to go into your array in most programming languages that start at 0 to identify the point. Okay, it's not bad to keep it here. How are we going to identify the y though? Y doesn't go by modulo. We are going to use the index divided by the number of columns. And we're just going to use the integer part of it. And so we go from 0 to 21, 0, 0, 0, 0, 0, 0, 1, 1. Of course, that's not the value we want. We want the actual y, but because it's increasing in a standardized way, we multiply that by our delta y. And again, we don't want to start at 0, but 0.1. That's so we want to add the so here we'll use the first term, index loaded area y, so the first term. Oh no, we start and it's minus, right? Because we start on positive in that one. 1, 2, minus 1. So we now have the coordinates that correspond to the terms. But it's not really what we wanted. We want to have the position x and y. And the thing is, we can use this from, using the same terms that we use here. Okay, so we could have another way we could do this actually. So here I did the mathematical operations, but it may not necessarily be what I want because I already have my values set up there. So another strat that I could use is I could use the offset. So I will use the modulo here, that doesn't change. But I will use the function offset. Offset of the variable x, loaded area x. Loaded area x. It stays on the same row because, so the offset function takes the upper left corner of a variable, right, of a range variable. And then you tell it the offset from that point, right? In terms of rows first. In our case, because the x is expressed as a single row, I will keep it as row 0, so 0 offset. And the column will be given by the modulo that we had before, that goes from 0, 0, 1, 2, 2, 2, 2, 2, 2, and loops back after 21. Okay. And I want one term, one row, and one column. So I just want one cell. And this should give me exactly the same values. Yes, so it gives me the same values, but this time it's instead of calculating the coordinates, it's looking it up in this range. Okay, so that's the difference of what I did in both cases. The first time I was calculating like I'm doing here, I'm calculating, and the second time I'm just searching. I will use the same trick now here. Again, it's the integer that I want. The integer gives me my offset, right? So because of that, I will use again my offset function. Of the variable loaded area y. And this time the row will be changing. So initially we'll take the top one, and then it will be moving downward, but it moves downward by the integer of the division. So it will stay on the same value for a while. The column does not change, and then I return one cell in one row and one column. So one cell, single cell, which is comma 1, comma 1. And I get exactly the same thing. So important thing to do to see here is that I use the offset command and I moved by integer of of the index over ncol or the modulo of the index versus ncol. So I will do the same thing, and this time I go to data area. Okay, so my data area is in 2D. So I will use again the offset command, and I will use both of these things. Offset data area, which is that single cell, 0011. Okay, so I just get my first quarter right now. I want to use the same value as this to move through the rows. I will use the modulo of the column. That will move the column, sorry. The column is the second parameter after the name of the variable. So this is the one I turn here. I put it comma. Okay. And for the row, I will use the integer division that we have here. And in most programming languages, you have not only the modulo, but also a specific integer division, so. Okay. So now, as you see, I have used the same mapping that I use for my references for X and Y. And it's looking at single cells in my loaded area and picking up the value that it has there. So I have the loaded area. So. Find this one. Yes. I gave them names in case I need it. So now we have the means to do some products or whatever we need to do. Because we have the so we have the X, Y, and load for each point. So what we need to find now is our the equation for Busne stress under a point. Okay, so we have the stress increase at any point under a load. And so for any point, we'll have to look at yeah, the distance. So here the little lowercase r is the distance to each of the points under the load. So ideally, um, R will change definitely in both x, y directions. We need to figure out what the stress is at any point along our axis symmetric plane. Well, we'll have to define x. Oh. Five last time? Same. Here, if we have and the depth. This. This. So what will we say at the um so now for each point, at each point, we need to refer to each of the points in the load. So I need to have I will need to have the horizontal distance to each of those points at each of the areas. So if I'm doing this programmatically, it's easier to be doing it than on a spreadsheet. obviously, because on the spreadsheet, we have to figure out at each location. So, I have 480 spots at each location, for which I have to find the, the radial distance to my location. Now, fortunately, the radial distance to my location is only dependent on my my x, the position x, because it's the distance in the xy plane. Okay, so I can calculate here what would be the R for each of these for each of these locations, right? Okay. I think we need to do the same thing, if I recall. We need to do, so what we did here for our load, I think we need to do it for our entire domain array. So we'll have to make sure that we know where we are. So if I do the same thing here, how many? So this one will be the row and Z, right? So let's call this row. And let's call this one Z. We will have here again our columns for domain and rows for domain. and row D. And row. This is, the columns will be, the columns of row. Okay. Row. I think I'm starting to be tired. Columns of row. Did I have color row? No, because I have. Yeah, row. Row, right? Rows of Z. So now we will do the same thing for the domain load. Or domain stress, de-stress. Yeah, it's de-stressful. So you see, it's becoming now important to start kind of expressing things in terms of arrays. It makes things a little bit easier. Okay, so I have the loads, now we have de-stress, we're gonna do the same thing. I'm gonna leave myself some row here, some room here for the index, X, Y, load, and the radius, the radial distance R. And we're going to have here X, Y, have index X, Y of the domain. Okay, so our domain has these values. So the max index for the domain will be number of columns for the domain times the number of rows for the domain, minus 1. So it's 91 times 17 minus 1. And we're using this basically to do the same thing we did here. Okay, so we're going to generate indices from 0 to the max. So 1546. And 46. There, max index. Okay. So we generate this just so we can find easily the x, y, and then re-express it in terms. So here we're going to transpose our loading coordinates. Okay. We're going to transpose it here to the x, y's, just so we can calculate the r. And then, based on the r, we will be able to find the increment of stress caused by each of those. So by having them, the loaded area in one direction and our domain in the other, we can now add the effect. So this is easier to be done programmatically, okay? Whatever I do by adding it there, when I'm programming, I would just have a loop, basically. And I would do it. I cannot do a loop when I'm using a spreadsheet, right? So this is the way that I do the equivalent of a loop by putting everything in a sequence. Both of them, one goes horizontally or by columns, the other one goes by rows. And so now I can add those in a loop. Okay? So that's what we're going to do. We're going to end up on this once we've calculated this and just discuss how we're going to set up the domain for time stress zero. Once we have our stress zero, then it's just a matter of next time we'll just finish the axisymmetric thing. But I thought that this was, because here you have the process you would have to do if you were programming anyways. Just remember that this would be a loop, would be much easier to be done programmatically. This is harder to do because we're doing it on a spreadsheet. Okay? It's doable, so I'm showing you the how you can fudge things around to be able to achieve some of those things on spreadsheet. But the principle would be very similar. So, yeah, we'll just will we have time to finish it? Well, at least we should finish. So here we'll put the, how did I call these? I did give them a name. Load index, right? So this is load index. Transpose. And we'll just find here what the oops. I'm gonna find R because X and Y, R depends on each one individually, so we'll have to calculate it. X, Y, and Z. No, this one, sorry, row. Yes. Call it X, Y. Y will be 0 in all cases. And Z. So I will be moving these. So I will have here X, Y, and Z. So the Y will always be 0, okay? But I will need it to calculate the distance R, okay? So the X will be equal to my rho. Okay, so I need to define X, Y, and Z so that I can do the calculations appropriately for the stress. Good. So I do need to define, so here Y can be a constant, so again, programmatically, it's just a constant. Here I can also remove that column and add just the value 0 later on. But just to see what we are doing here. So so what is the equation that we had here? That's what we have to start with. Start from this. So this was the equation we were dealing with. So that delta PZ is what I have here called QZ. Okay, what was L? So L is just the diagonal distance. That's it. While R is just in terms of X and Y. Okay, so it is so we have to match the coordinates. So we have 3/2 times 3/3 times 5 times a value of P, that is the load that is there. Basically, rho, I should give it the name, the local file, right? Times, and now we said Z cubed, so Z is which one? Z is this one. And we'll fix the column. That one is cubed. And we divide by something that we will raise to the power of twice 1/2. And now we have here to add R squared. So what is R squared plus T9 squared? So R squared is the distance. So it's not the square root because it's squared. So it's the two differences, the sum of the two differences squared, right? So it's difference squared plus difference squared. With the difference of what? The difference of the x's, so it's this one. Where I fix the column minus this one that I fix row. And the difference in y's, I could just So there, I would say 0 minus, and then it's dy. Or 0 squared. Right, plus z squared. So that the columns and rows are expected. That's that. Yeah, I use 0 instead of the y, so don't compare it for now, but I see that the equation for now looks okay. Oh. There we go. Thanks, Daniel. Hope there's a value that is not 0 in there. Of course, I have my coordinates. So I need to put my x's. So the x will be the values along the plane. So we'll have to use the row. And so we'll go row, and then go to a depth increment each time. Okay? So we'll do the same thing as before, so and then on columns. So we have this, the modulo of the index, and call so what's from 0 to 6. One, go from 4 to 91. Oh, the guy invert my name, my accident. And go here. Oh. One. 0 to 9. No. You lose it. Tell me we didn't lose it. We'll close what we don't need. It's when we run out of RAM, this is what happens. This one we don't need for now. We don't need. This one. Oh, no, no. Lost everything, guys. Lost the equation. Okay, that's okay. We'll start with we'll just be doing the indexing. We did the equation already. I'll fix it before we meet next time. Next time we'll have a nice starting point to complete it. So all we really want now is the indexing. We know we can get the equation. The equation is just basically taking this equation and applying. So for the x's, we said we wanted to have modulo this, oh, yeah, I had the wrong variable, right? And row should be in column. So n for e for 17. And row and top. Modulo index. And so and that's row plus one because the index function starts at 1. 45. That sounds good. That's the proper value for this. This will always be 0. Value of z is integer. Integer of this. And call b. It's divided by. Perfect. So we go index z plus 1. So start at 1, 0. Goes to 8, so we have the proper value here. So this is where we're going to be adding up. So this will be a sum, basically, of all the little influences. So the QZ will be our final value for the cube, and it will be just a summation of everything that's there. And that's why I said that expanding things that way represents a loop. We do a loop in your code if you're coding this. And the summation within your loop is what you get here. Okay. And so we said again that was oh yeah, we'll just leave it here. I save it, I'll upload it. And next time I'll fill this because it's the same equation we had. I'll just fill it up the next time we come and we'll finish. So this is just to get our starting stress. Okay, so it gets a little bit more convoluted when you want to do things, but I thought it was one way to show you how you can do on a spreadsheet what you would do on coding and how you can take just an image. I mean, again, for coding, you can have an image, a grayscale bitmap, for instance, where each point represents a coordinate. So what I have here on this load, all those points there could just be extracted from the color scale of a bitmap image, for instance, that we created. You can have a complex geometry, you define your boundaries of your bitmap, or assign, and now you have a means of looping through it and create your initial stress. Little tricks of the trade. Sound good? In that case, we'll leave it at that until next week. I will be uploading this. And we'll be able to continue next time, finish the axisymmetric problem. Just have a quick look, see how it compares to the 2D problem of a similar, so already you know it's gonna be less stress with depth, just from what we've seen. It will be nice to just compare at the central value with the 1D problem. So I'll see you next week then. Good.
It go on. Is this little first? This equation.
The little r is the horizontal distance. It's the distance between 2 points, but just on the horizontal plane. It's x squared, is the delta x squared plus delta y squared. Delta y squared. That's delta y squared. We'll look at it, I'll complete it in the file and we'll look at it next time.
In radial coordinate, or
Radial coordinates.